Welcome to EDU World Space.
Okay, so for this guy, we have 0.37921 arcseconds, and the distance to Sirius is d 1 over p, and that's 2.63 pc. And remember that this is just a unit of distance. So basically, this means that the linear size of the semi-major axis of the reduced mass semi-major is pretty much equal to A, which equals alpha times D. Plug everything in, and you get about 3.00 times 10 to the 12th meters. Now what we have to do is use Kepler's third law, which says that p squared equals 4 pi squared over g times m1 plus m2 times a cubed, and we get that ma plus mb equals 4 pi squared over g times p squared a cubed. And this is just about equal to 3.24 times the mass of the sun. Now, what else do we know? We know that ma times aa equals mb times ab. And we know that ma times 1 plus aa over ab equals 3.24 mass of the sun. So all that we have to do now is solve for the individual masses, ma and mb, using these equations. And when we do so, you should get that ma equals 2.21 m star, and mb equals 1.03 m star. Okay, and so that's how we can find the mass of each member of a binary system, and that's for part A. Now, what about part B? Well, remember that we have an equation for absolute magnitudes, and it looks something like this: 100 times m1 minus m2 divided by 5, and that equals L2 divided by L1. And with something that we call the bolometric magnitude of the sun being equal to about 4.74, it's pretty easy to solve for LA and LB. And when I do so, I get about 22.5 L sun for LA, and for LB, I get about 0.024 times L sun. And finally, for part C, to find the effective temperature of Sirius, we should use the Stefan-Boltzmann equation, which says that L equals 4 pi r squared sigma t to the 4th, and using that with r equals 5.85 times 10 to the 6th meters, we get that's approximately equal to 0.0084 r of the sun, and that's about equal to 0.917 r of the earth.